How's it going, everybody? As I told you in drill, I was going to record a quick video to kind of talk about this sidebar thing that I had and talk about considerations of interpretations depending on how you have your data coded. And so this is, I just copied the sidebar from the drill itself. And I added a few things here at the front end. But so if you're trying to look off your own drill, this will be a little bit different. So I added in this stuff here. But so the first thing I'm going to do is I want to I'm going to create some new condition variables. That one's going to be called condition -1/2, 1/2, and one's going to be called condition 0, 1. So whenever I run this line over in my bias data, I have condition coded as 1/2 and -1/2 just as it was before. And then over here I have it coded as 1 and 0. So we're going to look at the differences of interpretation depending on how you have it coded. And also we're going to look at why the grand mean wasn't the same as the overall mean and what that actually means. So I'm going to run two different models here. One that is regressing the baseline on condition coded as -1/2 and +1/2. And I'm going to call that mod condition 5 or 0.5. And then mod condition 0, 1 is going to be baseline regressed on condition that is coded as 0 and 1. So I run both of those models, and then I'm going to run the summaries, and I'm going to store those as objects called summary 0.5 and summary 0, 1, so we can go back and quickly reference those. And then I'm going to calculate some means here. So first I'm going to get the overall mean just by taking from the bias data frame, get the mean of that IAT baseline. For the group means, I'm going to get the means of each condition group. So I group the bias data by condition. And I use the condition.f because this is one of those cases where I like to know which condition it is instead of seeing, condition 0.5 versus condition of -0.5. Like this will tell me the condition of bias training group versus condition mean for no bias training group. So again, I'm just grouping those, and I'm going to get the group means for the IAT baseline. And then here, I'm going to take that group means variable that we just created, and I'm going to get the mean of those group means and create an object called mean of group means, which is just the mean of means from those group means. So after I run this line, right now, if I want to see my model summary for the ones that are coded 1/2 and -1/2, I can run summary 0.5 and get that summary. Summary 0, 1 will show me the summary for when they're coded as 0 and 1. I can see that my overall mean for IAT baseline is 0.47. Here, if I run group means, I can see my no bias training group, the mean was 4.35, and the bias training group, the mean was 0.498. And if I take the mean of those two means, I get a mean of 0.466. So going back to what we were talking about earlier, so what's analogous to the model that we ran in drill is this summary 0.5, where we see that our estimate is 0.466. And then our slope of 0.06277. So since this is coded as -1/2 and +1/2, as I was saying earlier, that this mean here, this intercept, is the grand mean. Now, that's not to be confused with the overall mean. So if we look at our just the mean of all IAT baseline scores, we see that our mean is actually 4.7, or excuse me, 0.47. And but our grand mean is actually not the overall mean for that variable. The grand mean is defined as the mean of group means. So if we check our mean of group means, we can see that's 0.466, just like our intercept in this model. Now, the reason that our grand mean is different from the overall mean comes down to the equivalence of group sizes within the model. So if we look at our bias data, we can see that we have 44 people in the bias training group and only 34 people in the no bias training group. So I'm going to give you a visualization of what that looks like, or how that impacts and why that's different. So if we don't worry about all these are crazy, they're in bad form. I put them all on one line specifically because I don't want you worrying about what's in the graphs themselves. These graphs are just for explanation. So here we have two groups. And these two groups are equal sample sizes. The size of the dot is the sample size. And you can see that the grand mean and the overall mean are both smack dab in between those two groups. Now I didn't put any x-axis values on here because it's arbitrary. This is just a conceptual explanation. But so as long as you have equal group sizes, your grand mean and the overall mean, which again is just the mean for that outcome variable, will be the same. If, however, we have unequal sample sizes, so let's say that this is one group mean and one sample size, and this group over here has a bigger sample size. Now this is showing two different groups here, so don't get thrown off by this. But basically what this is visualizing is that if this group over here is bigger than this group over here, and right now let's just look at the red one, because this is bigger, when you take the average of these two groups, this being higher than this will disproportionately weight or pull the grand mean higher than the overall mean. Down here, if you look at this blue line and the blue dot, if we have a bigger group that has a lower mean than the smaller group, then that will push the grand mean down below the overall mean. So as long as the sample sizes are equal, then your grand mean and your overall mean will be the same. But again, if it goes up this way, then your grand mean and your overall mean will be different. So if we cycle back and forth between these, you can see bigger sample size is going to push or pull your grand mean away from your overall mean. As long as they're the same sample sizes, then your grand mean will equal your overall mean. And so just as a demonstration, if we take our data frame, and what I'm doing here is I'm just creating a data frame called yada yada, where I am limiting it to just the bias training group, because again we have 44 in that one. So now I've created this yada yada data frame that has only the bias training. Now I'm going to take that data frame, but I'm going to limit it to only the first 34 rows, and I'm going to bind that with the 34 rows of no bias training. So when I run this line, now in my yada yada data frame, I now have 34 in each group. So now I have equivalent group sizes that they're perfectly equal. And I'm going to run the same model that we did before, regressing condition or baseline IAT on condition. And when I check the model summary of that, now it's telling me that my grand mean is 0.46078. And when I look at the overall mean of that IAT baseline score, you see that it gives us the exact same value. That now when the group sizes are perfectly equal, your grand mean and the overall mean are the exact same. If the and as you can imagine, the greater the disproportion between the two groups, the more that's going to push. So in other words, if you have 34 in one group and 35 in the other, like that's not really going to influence it that much. If you have 50 in one group and 100 in the other, then the overall mean, the mean of means, is going to be a rather large departure from those two things. So that's the most of the sidebar that I wanted to demonstrate is why your grand mean is not your overall mean unless you have equal sample sizes. But I want to get back to this portion right here, looking at the summary, depending on whether it's coded right here, the condition is coded as -1/2 and 1/2, and right here it is coded as 0 and 1. So what I want to really reinforce is that the key to understanding the general linear model and to understanding interpreting regressions is remembering that the intercept is the estimate, it's the mean, it's the prediction when everything else in the model is 0. So what it comes down to as far as interpretation is thinking conceptually, what does 0 mean? And in this case, again, up here where we have it condition coded as -1/2 and 1/2, the estimate is 4.66 when condition is 0. So in this case, it bumps one group up by a half and bumps the other group down by a half to make this 0, which is how we get the grand mean of these. Down here, however, where we have the groups coded as 0 and 1, our intercept is the prediction, the estimate for when condition is set to 0, which in this case we have a group set to 0. So if we look at our bias data frame and we see condition equals 0 for the no bias training condition. So if they didn't have bias training, then their condition is equal to 0. So when we look at this output right here, this is saying that this is the estimate when condition is equal to 0, or in other words, when condition is no bias training. So this is the mean. This is the mean or the prediction for a score for a participant who is in the no bias training group, and this 0.06277 tells us that when there's a 1 unit increase, or in other words, when condition changes from 0 to 1, or when you switch from no bias training to the bias training group, that estimate goes up by 0.06. As far as what the interpretation here is on this effect coded, which is when we have our negative half and positive half, that's known as effect coding. This down here is dummy coding. So dummy coding is 0 and 1. Effect coding is -1/2 and 1/2, or -1, 1, things like that. So again, when you're using effect coding, -1/2 and 1/2, the intercept is the grand mean, and the estimate for the slope is the difference between the two groups. So this is saying that the grand mean is 0.466, and that the difference between the -1/2 group and the 1/2 group is 0.06. Down here, this is telling us that the estimate for the no bias training group is 0.43, and that the bias training group is 0.06 higher than that. So I hope that that kind of helps clear up some of these interpretation issues. As we move on, that there will be other types of coding schemes that we can use, other ways of coding groups, especially once we move on to having more than 2 groups that we are analyzing, and how do we compare the difference between group 1 and group 3, or group 1 and 2 together against the mean of group 3. All those types of things are different coding schemes that help us answer different questions. So ultimately, the coding scheme that you use will depend on what's the question you're trying to answer, and the interpretation of these regression outputs depends on the coding scheme that you use. So again, in this effect coding, -1/2 and 1/2, our intercept is the grand mean, and the estimate of the slope is the difference between groups. If we use dummy coding of 0 and 1, the estimate is the prediction for the group that is coded as 0, and the estimate for the slope is when you move up a 1 unit increase from condition 0 to condition 1, how much do you expect it to go up or down? In this case, we expect it to go up, because those who had no bias training are predicted to have a score higher by 0.06. So that's all I have for this particular video. I hope that makes sense for most of you. If it doesn't, by all means, let me know. I will also post this script right here on Blackboard. But just know that you have to run this in conjunction with the drill 4 because we're pulling based on the variables that I already created in drill. I already had it in my environment. So if you only pull up this script and try to run it, then it's not going to run. So if you want to see this for yourself, and you'll just have to run the drill 4 corrected script, and then you can run this script and go along with it. Anyway, that's all for today, and if you have any questions, as always, just let me know.